So what is calculus and why do we take it? How does it fit into the classes we've taken in the past? So here's an example of what we've looked at in the past. We've looked at linear equations, polynomial equations. We've done things like finding the slope of a linear function. We have found the x and y intercepts of a linear function. We've found the x-intercepts and y-intercepts of a polynomial. Those are still important, but that's not the emphasis on calculus. So let me just delete a few things here. Let's just draw a circle. Now, if you remember circles, if you had a circle consisted of a center point, and then the circle is defined by all the points that are equidistant from the center. The distance is called the radius. And then we had a line which we call the tangent line. And the tangent line intersected the circle at one point. So here it's not tangent, here it's intersecting more than one place. Here it's just touching one place. And for a circle, the radius to a certain point on the circle and the line tangent to the circle are perpendicular to each other. So let's say we have a curve that looks like this. It's the black curve. If I were to ask you, from a linear standpoint, what is the slope of this line? Well, it's not straight, so it doesn't have a slope, a single slope. Then I might ask, well, what does a tangent line look to this surface, this line, compared to a tangent to a circle? So these lines here represent a line with a certain slope, a certain rise over run. If I bring this to the curve and I look at where that curve touches it just kind of like this, say at this point, what I can say is that this line, this straight line, represents the slope of the, well, actually it represents the tangent line to the curve. Let's look at another straight line here. So here's a straight line. Here's a curve. Again, if I bring it down to that curve, there'll be some point where I just touch the curve in one location. Now right here, it looks like it touches in multiple locations just because the change in slope is very small. But so at this point on this curve, this is the tangent line. And over here, this is the tangent line. This, if you looked at this line, it has a slope, and this line has a slope. And we would say in general, they're both positive slopes. The rise is positive when the run is positive. And this curve would have a higher slope than that slope. So that's the whole idea behind calculus, differential calculus, is when we talk about finding the derivative of a function, what we're doing is we're finding the slope of the tangent line to that curve at any point on the curve. And we want to find it as not just as a list of numbers, but as an equation. So if we start with an equation, what is the slope? So for example, this line has a slope of 3 because it's in the form y equals mx plus b. This is the y-intercept. Now here, when you have a curve, the slope changes, but there is something you can do to this equation and find out what the slope of the tangent line is at any value of x. So that's the concept of derivatives. And where is this important? Well, it's important in both engineering, physics, and also business, because from an engineering standpoint or physics standpoint, if this curve is like a trajectory, or actually if this is a function, this is the displacement as a function of time, the slope of the tangent lines is indicative of a speed or velocity. From a business standpoint, if this curve were to come up to a maximum and then come back down again, that maximum point is key to a lot of business analyses, maximizing profit. When you're trying to maximize or minimize something, then derivatives are necessary. So the other things that we're going to talk about, we're first going to talk about limits. We just kind of introduced derivatives. Limits are almost like evaluating functions, and a lot of times limits are just evaluating functions, plugging in the value of x to get the value of y. But there are some cases, in the special case of an indeterminate situation, an indeterminate function where the function doesn't exist, but the limit does exist. So let me just kind of give you an example of that. I'm just going to pause for a second. Okay. So I'm going to plot a function. So here we have an x-axis, y-axis. And normally a function just continuously varies with x and y, but there are some cases where the function is undefined at a particular point in space. Now let's give you an example of that. So if you had y equals x plus 3 times x minus 1 divided by x minus 1, this function is undefined when x equals indeterminate when x equals 0, because what you'd end up with is put x equals 0, you get 3 times 0 divided by 0 when x equals 1, and that gives you 0 divided by 0, which is called indeterminate. But you can see that if you come from the left-hand side to this point at x equals 1, the function exists, and you've come from the right-hand side, the function exists. At x equals 1, the function doesn't exist, but it's approaching some value, and that's the whole idea of limits. And in terms of derivatives, the definition of derivatives ends up with an indeterminate result, but we want to find out what the limit is. So limits are are important, necessary in terms of calculating derivatives. Now so let's skip all over that stuff. As far as the integral is concerned, what we're looking for there is to find the area underneath a curve, between the curve and one of the axes. Now we all know what the area of a rectangle is. It's going to be the width times the height. And we use that simple expression to ultimately calculate the area under a not rectangular curve. So here's an example. So this is a function, I think it's 4 minus x squared. Y equals 4 minus x squared. So let me just write that out. So it's a polynomial. The negative is in front of the x squared, so it points down. You can see when x equals 2, you get 8 minus... Actually, that is not... it must be 4 minus something like that. I'm not sure the exact form, but it's similar. It's something like that. That's not the important thing. If we wanted to know what the area was between the red curve and the x-axis, how would we do that? Well, one way to estimate it would be to make rectangles up and use the value of the function at some value, at some x value, and calculate the y value, and then assume a width of, in this case, 0.5. And then we'd evaluate the function at 0.5, find the height, take that height multiplied by the width from here to here, which is also 0.5. And you can see I can do that, use that same process for every point. And I'd end up with these rectangles, which when added up would be an approximation. These would underpredict. These rectangles would underpredict the area because you've got these little bits we didn't count. These would overpredict it because you've got these little parts above it. Now you can look at using different philosophies. You can have them all above the curve. You could have them all under the curve. So this would, let's just do that. So I could do, this one would actually be here. This would be similar to what we had before. So the left-hand part of the rectangle is the value of the function there. And then when you would get to this point, you would still use you wouldn't use the value of the function at the left-hand side, but use it at the right-hand side. And that way, every rectangle would be under the curve, and in this case, you would definitely underpredict the area. So there are different philosophies for finding the area using rectangles. Now, the whole idea of calculus is that we would increase the number of rectangles more and more and more, ultimately, so that you have an infinite number of rectangles. Of course, you can't have exactly an infinite number because that's also undefined or does not exist. Infinity does not exist. But you can take the limit, and that area, as you increase the number of rectangles, would approach the exact answer. It actually would be equal to the exact answer when you take the limit process. So limits are important in both taking derivatives and finding the area underneath the curve. So where is this important? Well, again, in physics, more so in physics and business, the area underneath these curves represents certain physical properties, specifically something called impulse, which is what happens when you have a collision between or interaction between two objects. So we did derivatives, which was also the interaction of a force with a body, and it accelerated and it moved at different speeds. So in this case, we're talking about another physics quantity.